Hello, I am Ehsan Jafari, an expert in membrane technology. Before we start learning this lecture, just a quick note. I am available for your private consulting, system design, troubleshooting, and procurement. If you need professional support for your business, just hit me up on WhatsApp. Now let's begin the tutorial.
Hello everybody and welcome to this presentation. In the previous lecture, you learned how to design a reverse osmosis system for brackish surface water using ROSA software. In the theory part, in the section 4, you learned how to design a reverse osmosis system in 10 steps. And in this lecture, I'm going to design a reverse osmosis system for seawater desalination using ROSA software and follow these steps in the designing. A case study with the following given data considered for this design. As you can see, the feed is seawater, TDS 35,000 mg per liter, SDI is less than 3 based on the pre-treatment in this system, and temperature is 20 degrees Celsius. The required permeate, as you can see in the right side, is 1200 cubic meter per day with TDS less than 200 milligram per liter. That this is in the range of drinking water. That means that the aim of desalination of this seawater is for drinking water, and the recovery for this design is 55%. As configuration, continuous flow considered for this system. Now at first you have to select the suitable element for this system. As you can see, TDS in the feed is 35,000 milligram per liter, and in this guideline located between the 30,000 and 50,000. And for this you can select SW30. I'm going to select SW30XHR, as you can see 440i, based on the elements in the ROSA software. Now you should calculate the module number. For this you can use this equation. In this equation, as you can see, the QAP has determined in the given data and is 1200 cubic meter per day. The membrane element area is also based on the selected membrane, and in our case SW30, the element area is 41 square meter. To determine the F, you have to follow this table. In our case study, the feed water is seawater with SDI less than 3. The design flux range for this case is 13 to 17. And the maximum element recovery for this case study is 14. Now we have all data for calculation of module number. To calculate the minimum module number, you have to consider 13, and to calculate the maximum module number, you have to consider 17 for F. In this case, the minimum module number is 72 and maximum is 94. To reduce the cost, at first you have to work with the minimum module number, that in our case is 72. If you consider 6 elements for each pressure vessel, the number of pressure vessels can be 12. In this case, we can design this number of pressure vessels in one stage and two stage. For design this number of pressure vessel, you can consider one stage or two stage. I want to design both of them. At first, I want to start with one stage and then continue the design with two stages to compare both in terms of energy requirement and other parameters. Let's get back to the software and start the designing. Now we start designing with the software. As always, as you can see in the project information page, you have to input the required information in this page. The name of the project, for example, for this project is Persian Gulf. You can also write some notes about this project. For example, feed seawater TDS 35,000 milligram per liter, STI less than 3. You have only one case, and in the project preferences, for example, analyze with Ehsan Jafari, company name IWRS, balance analyzes with NaCl, and unit for this case study is cubic meter per day, and pressure in bar, and temperature also is Celsius. In the feedwater data page, you should input your seawater analysis data, and for this, as always, you have to cross the specified individual solutes and input each of which. But in our case, we don't have it, and we have to work only with total dissolved solids. The total dissolved solids in our case is 35,000 milligram per liter. Temperature is 20 degrees Celsius. If you have some information about the pH, you can input here. Now you have to select the water type. In our case is seawater with TDS less than 3. And now you have to go to the next page, scaling information. As you can see, you have an error here because a complete feedwater analysis is required for scaling calculation. It means that if you need to analyze the scaling in your case, you have to input water analysis in the feedwater data, that you have to cross the specified individual state and input all the water analysis in this page. Now in our case, we don't have this information, and just we work with the TDS, as in our case is 35. At first you have to uncross it, and we go to the system configuration. The first information that you have to input in this page is the information for the permeate and recovery. For this, you have to click one time in the permeate flow or recovery, and you have this page. And for this, you have to input the information for the recovery and permeate. The permeate flow in our case is 1,200 cubic meter per day, and the recovery is 55%. Then recalculate and accept changes and close. Now you have this information in the system configuration page. Now the software tells us if you want to have a permeate flow with 1,200 cubic meter per day with 55% recovery, you need to have a feed flow with 2,182 cubic meter per day as feed flow. The number of stages in our case is 1. At first I want to design it with 1 stage and then with 2 stages. The element type in our case is SW30 XHR 440I. The number of elements in each pressure vessel is 6, and pressure vessel in each stages that we have only one stage is 12. And you can see in totally we have 72 elements in this stage. Now I want to analyze this system, and for this you can get a report in this page. In this report, as you can see, you have some important information that you have to consider them. For example, the feed pressure for this case is 79.80 bar. It's around 80 bar. And to produce this pressure, you need this energy. It means that if you want to produce 1 cubic meter per minute, you need 5.04 kilowatt hour electricity to produce this feed pressure. Now, if you want to reduce this energy, you have to change some parameters in your design to reduce the feed pressure. In the stage information, you have also the type of the element. You can see here the number of pressure vessel is 12. The number of elements in each pressure vessel is 6. Required feed flow for this case is 2181 cubic meter per day. Feed pressure is around 80 bar. We don't have any recirculation system. The concentrate flow in this case is 981.80 cubic meter per day. The concentrate pressure is a little lower than feed pressure due to the pressure loss. And the pressure flow is 1200 cubic meter per day. And the average flux is 16.99. It's around 17. This number is the maximum number in the flux range that we consider to reduce the cost with minimum elements. The TDS in the permeate is 110, that the required permeate in our case is 200 milligram per liter, and it's suitable. Now, if you look at the design warning, we have an error. Maximum element recovery has been exceeded. Please change your system design to reduce the element recoveries. For this element, the limit recovery is 14%. How you can find this number? If you look at in this table, in our case the feed water is seawater with STI less than 3, and we consider a design flux range between 13 to 17. The maximum element recovery in this case is 14. It means that the maximum recovery for this element to produce this flux is 14. If you look at the elements 1, 2, and 3, you can see the recovery is bigger than 14. And for the number 3, maybe that was rounded and that was more than 14. Now you have to reduce this recovery to remove this warning. To solve this design warning, you have two solutions. You can reduce the recovery or increase the number of elements in pressure vessel. In our case, we cannot reduce the recovery because the customer wanted the recovery to be 55%, and that's why we cannot reduce the recovery. In our case, we increase the number of elements in each pressure vessel and get a report again to see. Now in the software, I want to change the element in each vessel and increase it. You have to notify that the total elements in a stage has to be 72. Now if I change the element in each pressure vessel in 7 and decrease the pressure vessels in, for example, 11, now we have 77. And in this case, the cost for your project increases. Now, for example, if I consider 10, we have 70 total elements in a stage, and now you cannot produce the required permeate with these total elements. It means that we cannot consider 7 elements in each pressure vessel, and now I want to increase the pressure vessel to 8. In this case, with 9 pressure vessel in each stage and 8 elements in each pressure vessel, we have 72 elements in the stage. Now I want to get a report and continue the designing. Now in this report, you have to control the pressure and permeate TDS again. And as you can see, feed pressure is almost constant and permeate TDS in the suitable range. The information for the S stage, the pressure vessel is 9 with 8 elements. Feed flow 2182 cubic meter per day. Feed pressure 79 bar. We don't have recirculation. Concentrate flow 981. Concentrate pressure is 77.7 bar and permeate flow 1200 cubic meter per day. The average flux is around 17 and permeate TDS is 108. Now, if you look at the design warning, we don't have any error. It means that if you increase the element in a pressure vessel, the recovery will be decreased. And if you look at the elements 1 to 8, you can see the maximum recovery is 12%. But there is a problem because sometimes due to the limitation in the space, you cannot use the pressure vessel with 8 elements because the length of the system increased and you have to reduce the elements in a pressure vessel. On the other hand, if you look at this table, a system with 55% recovery and a number of serial element position with 12 to 14, the number of stages have to be 2 if you use 6 element vessels. In such a situation, you have to determine the ratio between the stages. To determine the ratio between the stages, you can use this equation. N is a stages number and in this case is 2. The recovery percent is 55%. The total number of pressure vessels is 12. And now you can calculate the first stage pressure vessel number. And if you look at this image, the number of the pressure vessel in the first stage is 7.2 that we have to round it to 7. And for the second stage is 5. Now let's getting back to the software and design it again. Now to increase the stages, you can use this stages in pass and increase it to 2. If you click on each of which, you can change the information. Now for this stage 1 and for this stage 2. Now let's input the information for stage 1. For stage 1, if you want to use the same element for both stages, you have to cross it. In this system, we want to use the same elements with SW30XHR 440I. For the stage 1, the pressure vessel is 7 with 6 elements. Now we have 42 elements in this stage. And for stage 2, the number of pressure vessel in this stage is 5 with 6 elements. And now we have 30 elements. And in total, 30 plus 42 as elements in the stage 1, we have 72 elements in total. Now let's getting a report and see the result. If you look at this report, You can see the feed pressure is increased a little. The previous feed pressure was 79 and now it's 80 bar. But if you look at the permeate TDS, the permeate TDS for the first stage is 69 and it's okay. But for the second stage is 241. But the limitation for the TDS in our case is 200 and it's increased. If you look at the design warning, we don't have any design warning. And the permit for the TDS, you have all the information for each of elements here. If you look at the stage 1, you can see it's the range that we want, but for the second stage, it's increased. It is important that we need the outline TDS for the permeate, not for the stage 1 and stage 2, because the permeate for the stage 1 and permeate for the stage 2 mixed together, and now we have a TDS permeate as an outline. To find this number, if you close the report, you can see these tables. In these tables, for the feed, concentrate, and permeate, that the permeate is number 7, you have information as flow, pressure, and TDS. If you look at the TDS for the number 7, that is the permeate, you can see the total permeate is 107.27. That is the range that we need. Now, if there is a limitation for the space and you cannot consider a pressure vessel with 8 elements, you can use this design with 2 stages, that stage 1 with 7 pressure vessels and stage 2 with 5 pressure vessels. In this case, we didn't have any design warnings and the feed pressure didn't change significantly. TDS in our case is 200 milligram per liter. That the result that determined with the software is 107 and recovery is 55%. Now, as an example, I provided this exercise with this given data. The feed is wastewater with TDS 3800 milligram per liter and STI less than 5 and 25 degrees Celsius as temperature. The required permit is 760 cubic meter per day with TDS less than 100 milligram per liter with recovery 70%. In the case study that also I have done, you can also change the elements and use another elements in the software and compare the feed pressure, TDS, and some parameters that which element can be operated better than the others. Now this lecture as the last lecture for the section 7 ROSA software tutorial finished. In the first lecture from this section, you learn about the ROSA software tutorial, some guidelines and standards. You learn how to design a reverse osmosis for brackish surface water using ROSA software, and in this lecture also you learn how to design a reverse osmosis system for seawater desalination using this software. Thank you for your attention.